Another way to graph quantitative data is with a stem and leaf display, or what some people call a stem plot for short. The basic idea in this kind of display is that if you look at your data, you might see that some of them have the same leading digit or leading digits, and you can group those observations together, and just in your graph you're going to write the common leading digits as what they call a stem, and then to the right of that you would write all the individual last digits for each individual observation, and those would be called the leaves. Now when you draw this graph, it's going to always have a title or a heading that indicates the who and the what of the data. Every graph that you draw should have a title or a heading indicating that. Then we're going to have a column of stems from those common leading digits of the data values. Then we'll have the leaves written to the right of each stem, formed from the last digit of each data value. Now these might be rounded values, and in some situations that's going to be advisable to do before you draw the graph. And then somewhere on your graph you're going to have a key which explains what the stems and the leaves stand for. These are good graphs when the data set's not too large and when the number of potential stems is at least 5. You don't generally want to go with fewer than 5. If the data are not rounded, then the data values will be contained in the plot, and you can recover the data from the plot. You could find measures of center and spread from that. Here's some examples. We had a study done by a sociologist in New Mexico who wanted to see how the life of a cowboy was working out. And these are the longevities of 32 cowboys that she studied around 1890. The youngest died at the age of 47. The oldest died at the age of 97. And there was one who died at 47, and 4 who died in their 50s. 1 died at 52. 1 died at 57, and 2 died at 58. 5 died in their 60s. 8 died in their 70s, 8 died in their 80s, and 6 died in their 90s. So those are pretty significant lifespans. Over here you see the key. The 4 with the slash and the 7 stands for 47 years, at which the age at which the cowboy died. You could answer lots of questions about the data from this. The graph looks slightly left skewed, but it's not a very strong skewness. You could find the 5-number summary from the data pretty well, just from the graph. The median is between the 16th and 17th observations. That would be 75.5 years. The first quartile is between the 8th and 9th observations. That would be 67 years. And the third quartile would be between the 8th and 9th observations from the top, and that would be 86.5 years. So the IQR is 19.5. 1.5 times that is close to 30. If you subtract 30 from 67, you get about 37. So the lower fence, while it's not exactly 37, is much below, quite a bit below 47. The upper fence is quite a bit above 97. So there are no outliers. You can make your 5-number summary and have a nice little description of the data without even having to go through the process of finding the mean and the standard deviation, which would be quite a bit of work. If you were to put all these, if you wanted to find those things, you'd have to put all those observations into your calculator, and it's a lot of typing and pretty much too much work. Now, in some situations, you're not going to be able to get this many stems out of the data if you just use 10-digit leaves. You know, here we've got the 40s, 50s, 60s, 70s, 80s, and 90s, and there are 10 potential leaves for each of these stem values. In some situations, you're not going to be able to make that many stems. For instance, if you look at Albert Pujols, in 13 seasons in Major League Baseball, he has hit a minimum of 17 home runs and a maximum of 49 home runs. And if you just use 1, 2, 3, and 4 as your stems, you'd only have 4 stems, and that wouldn't be enough. So what you can do is this nice little trick of splitting the stems, and that's what I did here in this graph, is I split the stems up. So for instance, the 40s, I broke up into the upper 40s, which go from 45 to 49, and the lower 40s, which go from 40 to 44. I did the same thing with the 30s. This stem represents values between 35 and 39. This stem represents values between 30 and 34, the lower 30s. We didn't have any observations in the upper 20s or any in the lower 20s, and then here's the 17 all by itself. Now, these two stems don't have any leaves with them, but they still have to be included in order to give a proper and realistic idea of what the data look like. You have to include stems that are empty if they are between the minimum and the maximum values from the data set. So that's an important rule to remember. So what we have here is 1/7 represents 17 home runs. The high was 49. You could find the median by counting up. Since there were 13 seasons, the median would be the 7th observation from the bottom. 1, 2, 3, 4, 5, 6, 7. 37 is the median. The first quartile would be the average of the 3rd and 4th observations. That would be 33. The third quartile would be the average of 43 and 46, and that would be 44.5. And the IQR would be 11.5. 1.5 times that would be about 17. If you subtract 17 from 33, you get 16, which is below 17. So that 17, even though it stands apart, is not an outlier according to the outlier rule. You can find the 5-number summary, make up a nice little description of these data based on what the stem plot is showing you. Now, stem plot is very useful for comparing distributions. If you have two distributions of data on the same variable, you can put these stem plots back to back. Here we always have the stems going out increasing as we go away from, or the leaves rather, going out to the right. They're increasing as we go away from the stem. It's possible to put leaves on the other side of the stem too, increasing as we go to the left. And that's what we did in this graph right here. We have push-ups done on a fitness test by 24 high school students. Over here on the left we have the boys. Over here on the right we have the girls. Okay, we have these stems 0, 0, 1, 1, 2, 2, and 3. And on the girls' side on the right, we had one girl who did 2 push-ups, one who did 7, one who did 8, up to one who did 31. And as you can see, the leaves are increasing as you go away from the stem. On the other side, we have the boys. Here's a boy who did 11 push-ups. Here's one who did 16, one who did 17, another one who did 17. On this side, the leaves increase as you move away from the stems to the left. And then you could make comparisons between these two groups. And later on, we'll revisit this example. We'll see if there's a significant difference in the average number of push-ups done by these two groups of students. The key is a little bit more complicated when you have these back-to-back stem plots. I took this line right here to be representative, and I wrote the 3/2/4. This stands for 23 push-ups done by a boy and 24 push-ups done by a girl. And there you have it. So that's a very useful device, and we'll use that quite a bit as we go through the course.